Okay, so welcome back to the second segment, and here are the answers to the questions that were posed. So I will not discuss them, but I'll just put them up for you, and then you can check. All right, so we really solved the problem uh, in the previous segment, and now we are going to think about how this will help us to write the program. Okay, so let's just take a review. So what do we know so far? So we define V of D to be the set of meters of duration D. And then we observed that V of 1 is the set containing just the sequence 1. V of 2 was a set containing the sequences 1, 1 and 2. And so cardinality of V of 1, the cardinalities are what we are interested in. Cardinality of V of 1 is 1 and cardinality of V of 2 is 2. And then we followed Virahanka's analysis, and that gave us this identity. The cardinality of V of t equal to cardinality of V of t minus 1 plus cardinality of V of t minus 2 for any d bigger than 2. And the goal is that we will be given a d and we want to compute V of t. Okay, so simple enough. Well, just to simplify notation, I will define f of d to be the cardinality of V of t. And what we know? Well, this is just simply f of d equals f of d minus 1 plus f of t minus 2, okay, for d greater than 2. And something like this is called a recurrence. Okay, so what is a recurrence? Well, here f of d minus 1, d minus 2, for all values of d bigger than, for all values of d really, say starting at 0 and 1, for starting at 1, okay. So these f1, f2, f3 are unknowns, and this is an equation which is relating this whole set of unknowns, okay. So a recurrence relates unknowns, for example, f1, f2, in a sequence to each other. Okay, so that's what this is doing. So this really is a family of equations. So this is saying f of 3 equals f of 2 plus f of 1, or f of 4 equals f of 3 plus f of 2, and so everything. Okay, so that is what we got from Virahanka's analysis. And we also got through our fooling around earlier that f of 1 is 1 and f of 2 is 2. Okay, so these are called the base cases typically. Now you may recognize this and this to be something which is more commonly known as the Fibonacci recurrence. Now it turns out that Virahanka first of all did this much earlier. Okay, so probably a couple of centuries before Fibonacci did it, and there is some evidence to believe that these ideas traveled to Italy from India through Arabs. So be that as it may, we could probably still be calling this not the Fibonacci recurrence, but the Virahanka recurrence, or maybe the Virahanka Fibonacci recurrence. But let us not get into that. We will stick to the commonly used terminology, and in fact, that's why I have used F over here rather than V. Okay. All right. So what is our goal? We want to know f of d given d. So you give me a number, whatever, 39, and I want to tell you f of 39, or I have to write a program to do that. Well, how do we do this? Well, we can write an iterative or a loop-based program. So from f of 1 and f of 2, we can calculate f of 3 using this recurrence. Then once we know f of 3 and f of 2, again, we can use this to calculate f of 4, and so on. Okay? Or we could also write a recursive program or a recursive algorithm, whatever. So what is the recursive algorithm? Well, so these are the base cases, and to calculate f of d, we calculate f of d minus 1 and f of d minus 2. And those will be calculated recursively. All right? Okay, so let's look at the iterative program. So first we'll read n, Okay, n is the duration we want uh, for the for the each of the meters. So we want to count duration, count meters of duration n. N is what we have been calling d so far. Okay, so this is a statement which says that I'm going to use an array f with indices 1 through n. Okay, so what is fi going to be used for? Well, it's going to count, it's going to be the count that we want. Okay, so number of meters of duration I. And here we are using indexing from 1 going to n. And it is going to be okay in this course. Okay, so yeah, we know that most languages like us like the indices to be going from 0 to n minus 1, but that's okay. I mean, these are minor things that we don't really want to worry about in this course. We want to worry about the more difficult, the harder things. And so these minor things we are going to gloss over. Okay, now f is going to be initialized in this manner. Only the first two elements are going to be initialized. And then for I equal to 3 to n, we are going to execute this statement. Okay. Now, I'm not using a particular programming language syntax. I guess I'm using indentation though. Okay, so I'm going to maybe use a pseudo Python syntax. Once in a while, I will use C syntax, something like that. But the point is that the intent of what I'm doing should be very clear. Okay, so it should be easy, it should be trivial for anyone who knows programming to take this and translate it into whatever language. And then finally, we are going to print f of n, right? So this is the method that we discussed earlier, and this is the answer. This is what we wanted, f of n. Okay, so I coded this up in C++ and ran it for n equal to 51, just some arbitrary number that I chose, and it ran in 0.25 microseconds. For n equal to 1000, it ran in 5.1 microseconds. Okay, then about 40 times it took. Then if I optimized, okay, if I use the optimization, so C++ has optimization levels, and O3 if I use, then things get dropped by a factor of about 2.5. Okay, so something like that happened. Okay, and then I coded it in Python, and this took a little bit longer, but for n equal to 1000, again, it was about maybe 20 times slower. Oh, sorry, this was about 20 times slower. So everything is about 20 times slower. So okay, so what is the point that I want to make? So the point that I want to make is that we wrote an algorithm. We coded it in different languages with different compilers, so to say, and we got different answers. Okay, so we are not, in this course, we are not going to be so worried about programming languages. Okay, we want to understand how good is this basic idea. So we will see that although these numbers are very widely different, there will be some trend that we can still observe. So maybe the trend over here was that in going from here to here, things actually did increase by a factor of 20. Okay. Now computers are not don't behave exactly as you would expect, because look, on my laptop there are so many other things that are going on. Maybe I just got a message during that time, so things might slow down. And even if I'm counting operations, okay, so you might expect that if I run this loop just 20 times more, then time should be 20 times, but well, your computer is a bit of a complicated beast. So it will be about 20 times as you see, but not exactly 20 times. Okay. So what I'm trying to get at over here is that this ratio seems to be constant. Okay. Not the exact numbers, but if I say that this is the algorithm and I want to know how good this algorithm is, then these numbers are not important. But what I could observe is that, oh, from going from n equal to 51 to n equal to 1000, the number is scaling up by a factor of 20, roughly. Okay. Oh, and there is one more point I should mention. Now, if I just use this array f, and if it's an integer array, then you will see that the numbers become very big very fast. So I'm going to use a double. Okay, so I'm going to use floating point, so I'm going to not have exact precision. And furthermore, even for floating point for n equal to 1000, things get really large. So I'm going to start off with very small numbers. Instead of f of 1 equal to 1 and f of 2 equal to 2, in my C++ code or Python code, I'm going to start them off with 1 into 10 to the power minus 100, 2 into 10 to the power minus 100. Okay, so then things will stay within the range of the doubles also. Okay, so these are things which we are not quite going to worry about in this course, but they are important when it comes to writing the program. Okay, now here is the recursive program. Okay, so it's as you might expect, if n equal to 1, return 1, n equal to 2, return 2, what we had written down. Otherwise, find f of n minus 1 and f of n minus 2 and add them up and return the result. Okay, and the main program is going to read the duration and then it's going to print f of d. So f of d will get calculated. Okay, now analysis of this is okay. So this is yeah. So let's see. Okay, so we ran this in C++ and the time increased for n equal to 3 itself in C++. It took 2.4 microseconds. When I went to 32, it went to milliseconds, and when I went to 51, it went to 144 seconds. Okay, so that is absolutely a lot. When I used Python, it started off with 80 microseconds and it went up to 0.8 seconds. And I didn't even run it for 51 because, oh, the time would be really large. Okay, and I don't even want to think about that. Okay, I don't want to wait for that long. Okay, so something is becoming very clear over here, right? So what is going on? So what is going on is somehow the time seems to be increasing a lot. If I increase by 19, the time seems to going up by a factor of about 1,000, or maybe about a 10,000 or 7,000, and going from here to here by about 10,000. And similarly over here. Okay, so what is going on? And one thing that we need to observe is that this is much worse than the iterative algorithm. Okay, so if we look at, if we are in the business of saying designing good algorithms, so we have an interesting case now. We have two algorithms, and one of them is much faster, much faster. And so that is really the kind of algorithm that there's this the slower algorithm we don't want to design, the faster algorithm we want to design. And we also want to understand why this is slower. Okay, so I'm going to again leave some questions for you, and after you have gone through those questions, I will in fact solve those, give the answers. Okay, so I think in CS 101, you probably have heard this notion of a recursion tree. So what is a recursion tree? It shows the calls made during recursion. Okay, so what do I mean by that? So it will show, say, if I'm calling f of 51, then I'm going to draw a circle with 51 inside it, and then it's going to make two calls. So it's going to have a line going to f of 50 and another line going to f of 59, f of 49. So here I have f of 51, then there's a line going to f of 50, and then from here there is a line going to f of 49. Okay. Now f of 50 is going to call f of 49 and f of 48. So underneath this f of 50, I'm going to have lines to f of 49. I will draw circles to represent f of 49, the call f of 49, and a circle to represent a call f of 48, and I'm going to draw these lines as well. Okay, so if you go on in this manner, you will have a picture of which call is calling which other calls. Okay, and it will grow like a tree, and so this is called a recursion tree. Now, already you can see that in executing this, while calling f of 51, while executing f of 51, f of 49 is executed. But while calling f of 50, also f of 49 is executed. Okay, so already we are wasting time. We are doing the same thing twice. Okay, so this is an explanation of why the recursive algorithm is slower, because it is doing work. And here you might think that, oh, it's going to do double the work, but no, 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 it's going to do actually much worse. And that is what you are expected to figure out in these exercises. So draw this recursion tree. Okay, so make this table, make this picture, or however you want to do it, and tell me how many times f of 46 will be called if the initial call is f of 51. Okay, that's the first exercise. And then the second exercise is to generalize this. So how many times does f of n minus k get executed if the initial call is f of n? Now, this is a bit of a tricky thing to prove. Okay, so I will the solution will contain a proof, but even if you just figure it out and don't get caught up right now in writing a very clear proof, that's okay. All right, but let me just suggest to you how the general proof might look like. So define n of k as the number of times f of n minus k is called when executing f of n. Okay, so then you can say, okay, so how many times will f of n minus k get called when executing f of n minus 1, which is clearly the first thing you do over here. And how many times will f of n minus k get called in executing f of uh, n minus 2, which is the second thing you do over here. Okay, so write it in terms of this notation and you will get a really interesting answer. And actually the really interesting answer will also come up when you work this out. Okay. All right, so the solution is going to be in the next video as usual. So do the examples to spot the trend, try to prove this, and I'm going to break this segment at this point.